Have you ever heard of the Monty Hall Problem? Imagine you're on a game show. You're presented with 3 doors. The first door, you get a grand prize. The second door, you get a small prize. The third door, you get a worthless prize. You get a goat. Well, it's not even a goat. It's just a picture of a goat that you can put on your refrigerator. But you don't know which door has which prize. So you select a door. You pick the first door. The host, trying to confuse you, opens door number 2. Behind door number 2 is the mediocre prize. He then asks, "Would you like to switch your guess?" There's quite a debate going on. Some people believe that the odds of you winning the grand prize actually increase quite significantly if you decide to change your guess and pick the third door instead of the first one. What is correct, though? According to Wikipedia, when the player makes the first choice, there's a 2/3 chance that the grand prize is behind one of these doors not chosen. Okay, so far so good. That makes sense. The claim is that when you change your assumption and you change your guess, the odds of winning actually increase to 2/3% chance if you change your guess. They have a nice little chart here making that claim, showing different options. This chart looks incomplete, overly simplified, because obviously there's not a goat behind both door 1 and door 2. So this doesn't make any sense right here. This chart is wrong. It's missing information, or it's got too much information, one of the two. Well, you got 3 configurations here that it's showing. Again, this does not seem correct. Bad mathematics. I don't know. Maybe the best thing to do is to put it to an empirical test and see if the odds are 50-50% chance, or if the odds are 2/3% chance that you should change your guess. Let's real quick write a program to run this test. Okay, I have here a C# program, and my Visual Studios is throwing some fits here. But I have a Windows form that I'm creating, and I've got some counters. I've got my prizes right here in an enumerator. I've got a random number generator. I'm counting how many total guesses there were. I'm counting how many mediocre prizes, this OK prize counter right here. I'm counting how many options I have to switch. When I divide that by the total guesses, I assume that is going to yield about 2/3, because if I pick the mediocre, then their host open the door for me, and we can throw out all of those guesses where I picked the mediocre prize, because in our scenario, the host opens a different door than what we guessed, and the mediocre prize was behind that door. So options to switch. That's 2/3. Should I have kept my original guess? And should I have changed my guess? Now remember, to get the odds for these, the probability, we take the should I have kept my guess divided by the number of options to switch, and should I have changed my guess by the total options to switch. So I've got a timer that this form has. About every 1/10 of a second, this function right here is going to fire. And first thing I'm going to do is increment my number of guesses. And then I'm going to update the label for that. I'm going to take my prizes, stick them in an array, and randomize the order they're in. My computer is going to make a guess randomly. It's just going to pick one of the 3 doors. If he selected the middle prize, I'm going to update that counter. I'm going to update the labels, and I'm going to update the probability. If he did not pick the mediocre door, then the rest of this code fires. I'm going to update the options to switch. I'm going to update the label, and I'm going to update the label for the probability. Then I'm going to decide, okay, did I originally have the correct door, or did I not? If I did have the grand prize under the guess the computer made, then I'm going to update the counter for I should have kept that door. And then I'm going to update the label, and then I'm going to compute the totals. Should I have kept my guess divided by the options to switch? If I guessed the wrong door, the bad prize, I'm going to update that counter. I'm going to update the text, and then I'm going to update the odds by computing the I should have changed by the number of options to switch, and push that to the label. Now, my intuition tells me that as I run this code, the computed guesses, the mediocre prize, I'm going to win that about 1/3 of the time. So that should give me a 1 in 3 result for the odds. The option to switch, since I've got 1 in 3 for the I picked the mediocre, the options to switch will be 2 in 3. And in our scenario that was presented, we don't care if we pick the mediocre prize, but I'm going to track it anyway. My assumption is that my intuition tells me that I should correctly guess the maximum prize on my first guess about 1 in 3. And therefore, when the host opens another door showing the mediocre prize and asks me if I should switch, my intuition says I should switch about half the time. I've got a 1 in 2 chance of being correct when I switch. The Wikipedia here is going against my intuition and saying that I should change my guess because I have a 2 in 3 chance. So am I going to see 0.5 for the probability, or am I going to see 0.66 for the probability? Yeah, as well, if I should have changed my guess instead of kept it, I'm going to update that counter, I'm going to update the text, and I'm going to update the probability label. So let's go ahead and run this and get some empirical evidence going. Hey, look at that. It's counting up really fast, the number of guesses, the number of medium prizes won. That's hovering around 1 in 3. That seems reasonable. Obviously, it's not going to be completely perfect, but as this number of guesses goes up, it's going to get, the probability says it should get closer and closer to 1 in 3. A couple thousand tests versus a couple million. I assume this is going to get closer and closer to 1 in 3, or 0.333. My options to change, again, it's going to hover around 2 and 3. That makes sense. Should I have kept my guess? It looks like empirically I am proving that it's hovering around 50%. It is 0.49, and I should have changed as 0.49 up. It's bouncing between 0.49 and 0.50. Looks pretty definitive to me that I should disregard the proof that Wikipedia gives, because the empirical evidence clearly shows my chances of guessing are a 50-50. Myself personally, when the host opens the second door and say, hey, you might want to switch your guess, my intuition tells me that there might be some other variables at play that I'm not dealing with in this little test right here. Going by sheer probability, assuming that every time I guess either the worthless prize or the grand prize, the host is going to show me the mediocre prize, the middle prize. Under that assumption, it's clearly demonstrating that I have a 50-50 chance of being correct. However, I've got to wonder, why is the host trying to tempt me to change my answer? I mean, if I would have picked the goat to begin with, would the host have opened the door to the goat and say, ha ha ha, you guessed wrong? With that under consideration, I am inclined to keep my guess, even though the odds, under the assumption that he's not just going to open the goat on me and give me the bad prize, under that assumption, the best I have is a 50-50. Now, there's another assumption that could be made. What if the host always really like to help the contestant out? Now, that one makes a little sense, I guess. So, is the host the kind of guy that likes you, or the kind of guy that wants to keep the prize for himself, or the kind of guy that's just trying to keep things exciting for the audience? All variables to try to consider that aren't involved in this little experiment, and could drastically impact your probabilities. But under the assumption that if you don't guess the mediocre prize, the host is going to open that door on you and leave you with the choice between the other two prizes, the empirical evidence clearly shows that most people's intuition is correct, and it is a 50-50 at best. It's none of this 2 and 3, 1 and 3 crap that Wikipedia is trying to argue. Empirically, it is clearly a 50-50. I hope that there's other people that actually run this experiment empirically and demonstrate that it's easy to fool people with false proofs and mystery math. You guys have a wonderful day.